Hello and welcome back to another stormy day in Thailand. We are well in the middle of rainy season now. What I want to talk to you about today is yet another new project for Mikey, and it centers around my favorite new microcontroller, the ESP32. Now, there are a lot of ESP32 boards in the market right now, and I'll show you a bunch as the pictures go by. But I always found them to be somewhat lacking in one respect or another. So I decided to come up with my own set of requirements, and naturally, I made a circuit board for it. So what am I really looking for in a development board? This is not an end product thing. This is a board with which I would do prototyping or build little experiments before I committed a particular circuit to a circuit board. So it's got to help me in all the things that a hardware and software developer needs during the prototyping phase. So what does that mean to me? It means USB with the ability to pass both power and data. It also means, next to that, the ability to flash with an FTDI board, because I've used that quite extensively and I like it a lot. It means an onboard 3.3 volt power regulator to bring down the USB power from +5, and also make that 3.3 volts available to other parts of the circuit to the extent limited to which the regulator can output a certain amount of current. Next, I want to have every pin access to the native ESP32 module. A lot of boards don't give you every pin. I want every stinking pin. In addition to that, I don't want to have to be constantly looking at a data sheet or making notes to myself as to which physical pin connects to which GPIO output, connects to which UART, and which touch sensor, and which digital to analog converter, and which analog to digital converter. So basically I want every pin labeled with every function that it can possibly perform right on the board. So at a glance, I know I'm plugging the wire into the right little socket, and I'm writing my software to talk to the right function. In addition, as I've personally discovered, and as was confirmed on a YouTube video by the man with a Swiss accent, that the analog to digital capability of the ESP32 is just garbage. It is not accurate enough to really effectively base any native design on the ability to understand what input voltage you're reading. And I don't understand why Atmel and the ESP32 guys at Expressive, how they get away with this. Why would you put a piece of crap ADC into your design? Just do it right. It cannot be that hard given the amount of silicon needed to do it on the die. When you have chips like the ADS1115 is brilliant. It's really accurate. It reports its outputs over the I2C bus. It's got 4 channels. So basically what I did is I integrated that chip onto the board. So you automatically get 4 channels of high precision analog to digital control without any additional circuitry for that little teeny tiny chip. But if you're going to put it into your end design when you commit to a circuit board for your project, then it's good that you've already proven everything out. You've got it set up in the software, you're reading it in the software, and you're wiring it up to in the hardware. Couldn't be better. So, of course, there's no board that I've been able to find that satisfies all those requirements. So I threw a design together, uploaded it to JLCPCB, and here it is. So here's the circuit. It's pretty straightforward. At the heart of it is the ESP32 W room module. Room, I keep thinking to myself. I don't know why they've chosen this name for the product. And you can see that most of the pins, they go straight to 2 rows of jumper pads, which are lined up on the sides of the board. We also have our USB input over here through the CP2102 USB chip to the UART0 of the ESP32. Dead straightforward, with a couple of LEDs that show USB activity. Over here is our voltage regulator. Takes USB power in, puts out 3.3 volts to power up the ESP32, and it's got a power LED. We've got a reset button over here, and we have a flash button. Now the flash button is tied to GPIO0, and this is required when you're using FTDI to flash firmware into the ESP32. Some boards allow you to wire I think it's the DTR pin of the FTDI board to GPIO0, which will pull it low at the beginning of a firmware update. I've found that not to be particularly repeatably accurate, so I decided to put a button in there, and then I just push that and then start my upload. This is the FTDI pin right here. It has its own dedicated Blinky LED, and then down here is the ADS1115 chip. That's your 4-port, highly accurate analog-to-digital converter, which reports its output over the I2C bus, or I2C bus as I call it sometimes. So if we pop out over here to the circuit board, this is it. You can see by the flood of color that I've put extensive ground planes on the top of the bottom. Let me remove those, and you can see how the board's laid out. Chips in the center. We have every I/O pin going down the sides. We have our USB input here. We have our USB data chip here, our activity LEDs here. Our FTDI pins are here. The reset button and flash button are down at the bottom, and this is the ADS1115 4-channel analog-to-digital converter. Now, the important thing to see is every pin is labeled with every possible function that it's got, raw out of the ESP32. So this is GPIO27. And I have a legend up here. So GXX is GPIO pin XX. DI, digital input. DO, digital output. DP, digital output with PWM, pulse width modulation. ADC X.Y is ADC number X and channel number Y. Digital to analog converter X, UART X, and touch pin X. So that gives us what we're doing here. So this is GPIO27. It can do digital output. It can do digital pulse width modulation out, digital in, and it's analog to digital converter number 2, channel 7, and it's also touchpad pin 7. So with a glance, I know exactly what that pin can do. Also up here are some notes for the developer. When you're using Wi-Fi, a lot of people don't get this until it bites them. ADC2 is disabled. So you're only getting one analog to digital converter unit when Wi-Fi is active. Now, +5 is coming in from USB, and I'm making 3.3 volts through the voltage regulator right here. So I'm just saying there is limited +5 and limited 3.3 volt supply if you choose to take that off and power up other parts of your circuit. And the ADS1115 chip on the I2C bus is at address hex 48. So whenever you want to play with this, you work with your software, initialize it at hex 48. Now the ADS1115 chip is right down here, and it also has 2 jumpers. If you put these jumpers on, then this chip is going to talk across the I2C bus to the ESP32. If you leave the jumpers off, then you have allowed GPIO 21 and 22 to use them at your wish, whatever their native function is that you want to access. But if you're going to use this ADC chip, you must put the jumpers on, and then these two GPIO pins are dedicated to the I2C bus. So here's how the board came out, and you can see I chose the black PCB material so that the white on the silkscreen would stand out really well against it, and I think it does a great job. The text is actually readable. I don't know if my camera's going to focus on that, but trust me, it's human readable. It's quite good. The only downside is I forgot to do the setting on my Gerber export where it put the solder mask over the top of the vias. So you can see for the via holes, I can get my pointy thing, the vias remain silver solder and the silkscreen does not cover that at all. So I'm missing out on some of the legend, but for some reason the vias are covered up on the back but not the front. So the next rev of the board I do, I'll set the setting to put the silkscreen completely over the vias, and then all the text will be very readable. The board is 75 by 70 millimeters, so it's pretty small. It's like about the size of the palm of my hand, so it should be easy to work with on a breadboard. And it's got all the pins down the side for easy jumpering over to whatever you happen to be working on. It's got the USB plug in the top and FTDI here, and it's got the jumpers for the I2C bus here and the reset buttons. So it should be fairly convenient to use as a prototyping board. So the next step is to spread some solder goo on this with the stencil I got from JLCPCB, which will go like something like that, and then we'll put the parts on and fire it up. After spreading the solder paste, I hand placed all the components down on the board. Everything is looking pretty good. I still hate that little USB chip. I hate you. But all right, let's heat her up with my air station, see how she works.
And the lamp blazed forth in unparalleled glory. Oh, look at that! When you look at that, isn't that glorious? It's indescribably beautiful. It reminds me of the 4th of July.
Okay, all leg lamp jokes aside, I'm really happy with the way this turned out. The soldering with the hot air station went well, except I had 2 of the USB pins were bridged right there, which I just flicked with my soldering pencil as I was doing the connectors down the side and here and the jumpers. Even that damn little USB chip might have actually turned out okay. I buzzed power and ground, there's no shorts, but I am not going to power it up until tomorrow. I'm going to sleep on it, and hopefully in a dream, maybe I will remind myself that there's something wrong that I need to fix. Otherwise, it's smoke test in the morning. Okay, it's the next day. I slept on it. I didn't have any bad dreams. So it is go time. Now I've instantly realized my first problem, that the USB micro socket is far too far away from the edge of the board, but the PCB layout that I downloaded had it going right to the edge. So that's my first mistake. So I dug through my massive collection of USB wires and I found the one with the longest plug on it. So let's see if there's any magic smoke. Framing. 3, 2, 1. Contact. Oh, we have power. We have boongity boong, which means the PC recognized a USB device, which is pretty fantastic because that means that damn little chip right there may be talking correctly. And if I look at my little USB current sensor, it's pulling about 100 milliamps, doing nothing. So that's good. I don't see any smoke, anything hot. No, nothing's hot. what I'm going to do is write a short Arduino program that blinks the Blinky LED just to prove that things are working. Well, wouldn't you know it, my first test with the Blinky LED, I got no Blinky. Only to realize I soldered the LED on upside down. If it's a 50-50 chance, I'll pick the wrong 50. But we are blinking an LED. The board is alive. Yay. Okay, let's wrap this up. I'm going to do another series of videos about different aspects of the board and lots of sample code to drive all the functions. So, big thumbs up. Thanks for watching. And let me know in the doodly-doo down below if this is the kind of thing you might want to buy for your own development. Haven't decided if I want to turn this into a product. It was basically just for me. But if you think that this can help you, let me know. We'll see what we can work out. I'll maybe do a small batch run. I've got all the parts from the LSSC catalog, so I can get JLCPCB to do as much of the initial soldering bits as I can. Probably leave me with the module and the connector strips around the side and the little jumper wires, but we'll see. It'll get me 95% of the way. And here's a small little bonus for people who have hung on till the bitter end of this video. My name for it right now is ESP32 Protoboard, which reflects my complete lack of imagination. Now, I've seen a lot of other little project boards like this in the past that have really cool, snappy, cool names. And that's what I'm shooting for. So if you can think of a cool name for this, put it down the doodly-doo. And if you convince me to give it your name, you get one for free. So I'm throwing down the gauntlet. Okay, signing off. Bye-bye. Hey, if you found this video interesting, please give it a thumbs up. And if you like my other content, I'd appreciate a subscribe. Take care and see you next time.